Hey guys, this is a video solution to the red light whiteboard problem, which is an application of conservation of two-dimensional momentum. So I'm driving my Subaru Impreza through an intersection. I'm traveling west, and I go through at 45 miles an hour. Somebody else, an irresponsible Florida driver, is driving his new Audi R8, going north, so he's going to go through at a right angle with respect to me. He hits me, and our cars stick together after the collision, traveling at an angle of 65 degrees north of west. How fast was he traveling before he hit me? And then how much energy was lost during this collision. So I'm going to be as careful as I can doing this problem so that you can see conservation of momentum in a very clear format so you can reproduce it on the exam and on your homework. First thing I want to do is I want to write down all of my knowns and unknowns. There's the mass of the Subaru and the mass of the Audi. The initial speed of my Subaru is 45 miles an hour. That's 20.118 meters per second. I don't know the initial speed of the Audi, and after we go through the collision and stick together, I don't know our final speed. And I also know the angle that we travel after the collision is right here. I should probably label this arrow PF, so that's the final momentum after we collide. So this is an inelastic collision, being two cars colliding, so we can't use conservation of energy, but we can use conservation of momentum. We can always use conservation of momentum regardless about conservation of energy. So delta P equals 0. Delta P, the definition of P is just the momentum, so we can rewrite this as our two equations, Px final minus Px initial, that's equal to 0, and Py final minus Py initial equal to 0. Our x and y directions are defined right down here. I can put in the initial velocities for the two cars in here as well. Okay, good. So the next thing is to just rewrite the momentum equations in terms of the symbols that we have defined up here. I don't even need to start setting things equal to 0 or start to do anything else like that. I just need to write them in terms of these symbols here. So I'm going to do that. So here are my two momentum equations. First, the x direction, which comes right from here. This should be all the final momentum in the x direction. They're moving together, so this is going to be the same for both of them. Of course, it's just in the x direction, so this is VFX, and A and B. This is the initial momentum, the initial velocity in the x direction of the Audi times the mass of the Audi, and the velocity in the x direction of my Subaru times the mass of the Subaru. This is the same exact equation, except in the y direction. I really haven't done anything related to the problem yet. I've just identified that it has some final velocity, and this is the x component of that right there. And I've identified that it has some initial velocity, and the x components work out like this. I have said that the final velocity of the two objects will be the same, but that's the only simplification I made that's specific to this problem. So the next thing to do is to take our equations here, look at our given information, and then use our given information to the equations. But of course, they're not in the right form yet. I have this initial velocity of the Subaru in the x direction, initial velocity of the Subaru in the y direction, but I only have the total speed of the Subaru. So I need to split the initial velocity of the Subaru and the initial velocity of the Audi into components in order to put them in this equation. I can't just take the magnitude and put them into here. This is only in the x direction, and this in general will be in both and the x and the y direction. Of course, in this case, it's a little bit simpler because this right here is only in x, and this is only in y. So that means the velocity of the Subaru in the y direction right here is 0, and the velocity of the Audi initially in the x direction is 0. So that also means we can isolate a little bit what we're looking for. We actually want to find this, the speed of the Audi in the y direction, and this is actually going to be negative VSI. Just because the way that I set my coordinate system up is that VS is going in the negative x direction. This is a speed, so in order to make it the x component, I have to put a negative sign in. So now we'd like to try to solve this thing. We have one unknown, but it looks like we have two more unknowns, VFX and VFY. So it looks like we have 1, 2, 3 unknowns and 2 equations which we can't solve. But of course, these things can be rewritten in terms, these are the components of the final velocity, they can be rewritten in terms of the magnitude of the final velocity because we know what that angle is. And so what I'm going to do is I'm going to break up this momentum into the x and y components. And I put the negative sign on the PF cosine theta because we know that thing is going to be in the negative direction. And now I can rewrite these guys in terms of that x and y components. I'm also going to recognize that I have a VFX and a VFX here, so I can just pull that out and get an MAMV times the velocity. Okay, so now this is what I have. I made this positive because I had a minus sign here and a minus sign there. And in the y equation, I just ended up with VF sine theta from right there going into there. So now I need to eliminate. You can see that I've corrected my problem of having 3 unknowns. I now have only 1 unknown because I know what that angle is. It's 65 degrees right there. And I don't know this. So now what I'm going to do is I'm going to eliminate VF from these 2 equations and solve for this. I'm going to do that by first solving this equation. So I could plug some numbers in to get that out, but that's not going to be overly important for us at the moment. This is the final velocity, this final speed of the 2 cars as they go off at an angle of 65 degrees. But now I can take that and plug it back in right here and solve for this thing. Here I'm just rewriting the sine over cosine as a tangent to make things simpler. And there is my final expression. The ratio of the masses times the initial velocity of the Subaru times tangent of the angle. Numerically, 34.97 meters a second. Most people did this out in miles per hour, and the answer is 78.23 miles per hour. So that's how hard I got hit by the Audi. Part B of this question asks how much energy was lost in the collision. It's an inelastic collision, so energy is not going to be conserved. So we're going to have some delta K, which is not going to be equal to 0. The definition of delta is essentially F minus I, so I'm just writing delta K is KF minus KI. In the final state, the 2 cars were stuck together, so they're going to have a total mass and 1 speed. In the initial state, they were separate, so they were traveling at separate speeds, so I need 2 terms in my kinetic energy equation. And I already found the initial speed of the Audi. I know the initial speed of the Subaru. I don't know the final speed of the Audi yet. But as you saw on the previous slide, I actually solved for this halfway in between, so I'll find that now. That ends up being about 21.3 meters per second. And then I can just plug all my numbers into the kinetic energy equation here to find the change in kinetic energy of the 2 cars. Final answer coming out of my calculator is negative 612,000. That'll be in joules because everything is in SI, and you can probably write that as negative 0.612 megajoules. So like 500,000 joules is how much I lose. You know it's a loss because that's negative, which is what we expect. We expect the cars, when they collide, the crumple zones absorb the energy of the collision so that the drivers are less injured. And we end up with a loss of energy because this is an inelastic collision and we should expect there to be energy losses. Okay, great. So that's the solution to the two-dimensional momentum whiteboard problem. This is important stuff. Conservation of momentum is a key component of this class. So I hope this solution has helped you see where your errors are and help you to work out conservation of momentum in a more organized fashion so you can be sure to get the right answer when on the exam. Okay, great. Thanks for watching, and I'll see you guys in class.